Say a word out loud, any word. By the time you hear it, it is gone, the sound spent, the moment sealed behind you. That is the one rule everything seems to obey. Each instant happens once, never again. A theorem in physics says this is false. Wait long enough, and the moment you just lived returns. Exactly. Getting there takes a prize awarded to a broken proof, a fight over a box of gas, and a number too large for the universe to hold. First, the claim itself, in full. In 1890, a mathematician in Paris proved, not proposed, proved, with the finality only mathematics allows, that any sealed, finite system must eventually return to the exact arrangement it started from. Not an arrangement like it, the same one, to any precision you demand, and not once, but endlessly, as many returns as you have patience to count. His name was Henri Poincaré, and the result is called the Poincare-recurrence-theorem. Apply it to a box of gas, and it says the gas must revisit every configuration it has ever passed through. Apply it to a universe, if a universe qualifies, and it says something it takes a moment to absorb. The arrangement of atoms that is you, saying that word, must assemble again. The modern calculation of the waiting time produces the largest finite number ever used in a physics paper, a number so far beyond anything countable that it makes no difference whether you measure it in seconds or in lifetimes of the universe. We will meet it tonight, and we will write it down in the only way it can be written. Hold on to the word you spoke a minute ago. By the end of tonight, you will be able to say exactly what physics thinks happens to it, and the answer will turn on one thing hanging in the night sky right now. What does the theorem actually claim? Start with what it does not claim. It does not say history will rewind, like a film played backward. It does not say you will remember anything, or that anything continues from now to then. It says something colder and stranger, that a sealed, finite system, left to run under laws that conserve its energy, cannot invent new arrangements forever. Sooner or later, it must come back to an arrangement it has already worn, as close to the original as you care to specify, and having done it once, it must do it again and again without end. Why would that be true? What forces a system to repeat itself? The answer comes down to a single idea, and it is the idea this whole night rests on. The system has only so many places to go. Picture a deck of cards. 52 cards can be ordered in about 10 to the 68 ways, an 8 followed by 67 digits, more orderings than there are atoms in our galaxy. Shuffle once per second, and you will not repeat an ordering in the lifetime of 1,000 universes. But the number of orderings is finite. It is a fixed catalogue. And a shuffler who never stops, drawing from a fixed catalogue, has no way to avoid repetition forever. Eventually, absurdly, unimaginably eventually, a shuffle must land on an ordering the deck has already worn. Nothing mystical arranges this. Arithmetic does. You cannot draw endlessly from a finite catalogue without drawing the same card twice. Physics has a name for that catalogue. It is called phase space, and it is the single most useful picture in this story, so it deserves a full minute. Take the box of gas. To know its exact condition at one instant, what would you need? The position of every molecule, 3 numbers each, and the velocity of every molecule, 3 more. For a box with 1 trillion molecules, that is a list of some 6 trillion numbers. Now imagine a space with that many axes, 1 axis per number. The entire box, every molecule of it, collapses to a single point in that enormous space. 1 point, 1 exact condition of the whole gas. As the molecules fly and collide, the point moves, tracing a path. The full history of the gas, every jostle of every molecule, becomes one line wandering through phase space. Physicists call each exact condition a microstate. Your body, this room, the planet, at this instant 1 microstate. The question of whether this moment can return is the question of whether that wandering point can come back to where it is right now. So what did Poincaré prove about the wandering point? 3 conditions and then a guarantee. First, the system must be bounded, finite energy, finite room, so the point cannot drift away to infinity. Second, the flow must preserve volume in phase space, a technical condition we will unpack in a moment, because it is doing the real work. Third, the laws must be reversible, running as lawfully backward as forward, which the mechanics of particles does. Grant those 3, and the guarantee follows. The point returns arbitrarily close to its starting condition, infinitely often. Keep a hand on that first condition. Bounded, sealed, closed. The entire final act of tonight turns on whether the real universe honors it. What is this volume-preserving condition, and why does it matter so much? There is a theorem behind it, proved by the French mathematician Joseph Liouville decades before Poincaré used it, and it says this: take not one starting point, but a small cloud of them, a droplet of possible starting conditions, and let the laws of motion carry the droplet along. The droplet will stretch, fold, filament into wisps of extraordinary complexity. But its volume never changes, not by 1 part in a trillion. The flow of physics through phase space behaves like an incompressible fluid. Picture a drop of dye in slow, thick glycerin, stirred forever. The dye draws out into threads fine beyond seeing, but not 1 cubic millimeter of dye is ever squeezed out of existence. Whatever volume of possibility you begin with, you keep. Why does incompressibility force a return? Here is Poincaré's move, and it has the brutal simplicity all great proofs share. Take the droplet of starting conditions and follow it. Time never destroys volume, Liouville guarantees that, so as the ages pass, the droplet sweeps out more and more territory, all of it the same size per step, none of it ever compressed away. But the territory available is finite because the system is bounded. A finite room cannot host an endless procession of equal-sized, never-overlapping guests. Sooner or later, the swept regions must intersect the original droplet. And the instant they do, some condition inside that droplet has come home, a microstate has returned to its own beginning. The measure of conditions that never return, Poincaré showed, is exactly 0. In the mathematician's language, almost every state comes back. Almost every moment recurs. Notice what the proof did not need. It did not need to track a single molecule. It did not follow 1 collision. It counted rooms and it counted guests, and it found the guests must eventually double up. That is why the theorem is so hard to escape. It does not care about the details of the dynamics, only that the dynamics conserve volume inside a finite space. Any system meeting the conditions is caught: a box of helium, a swarm of stars, a planet of 8 billion people, if they are sealed in and finite. Take a moment with that. Before tonight goes anywhere else, consider what has already been established, because it is the part most retellings blur. This is not a speculation about far futures. Within its premises, it is a theorem, as solid as anything in mathematics, published under the scrutiny of the best mathematicians of the 19th century, and never overturned. If the conditions hold, the conclusion is not likely, it is mandatory. And the conclusion has teeth. Open a perfume bottle in a sealed room, and the scent spreads until the room smells faintly and evenly of it, the most ordinary, most irreversible thing you know. The recurrence theorem says, wait, and every molecule of that perfume must eventually find its way back into the bottle at the same instant, reassembling the sharp, full scent of the moment you opened it. Wait longer, and it happens again. The air you are breathing now, the theorem permits stranger things still, and later tonight we will watch 2 of the most respected physicists alive walk through what it permits. All the air in your room, every molecule, gathering by law into one corner, into a space smaller than a sugar cube. Why? Simply because that arrangement is in the catalogue, and everything in the catalogue must be visited. Given the conditions, this is not a possibility. It is an appointment. What does it mean that the moment you are living now is, on paper, a repeating event? An arrangement the universe is required to wear again, the way a clock is required to show noon twice a day. Sit with the question, because everything in you resists it, and the resistance has a name. You have watched an egg break. You have never watched one unbreak. You have watched cream swirl into coffee and vanish into an even tan. Never once has the tan spontaneously unmixed into white spiral and black liquid. Everything you have ever seen runs one way: order into disorder, sharp into smooth, hot into lukewarm. Physics agrees with you, and it agrees in the form of one of its most famous laws, the second law of thermodynamics, the rule that disorder, measured by a quantity called entropy, always increases in a closed system. Always. And there lies the problem, stated as plainly as it can be stated. One result, the recurrence theorem, is proved. A closed, finite system must return to its ordered beginnings. Another law, the second law, is confirmed by every experiment ever run. A closed system slides toward disorder and stays there. Both cannot rule the same universe. Can they? That collision is not a footnote. It detonated in the 1890s as one of the fiercest and most personal disputes in the history of physics, between a mathematician armed with the theorem you just watched proved, and a physicist who had spent his life building the theory of entropy. A fight over a box of gas, conducted in the pages of the leading physics journal of the age. At stake, a career and, some historians argue, far more than a career. The resolution they groped toward is subtle, beautiful, and still quoted in papers published this decade. To understand who was right, and the strange sense in which both were, you need to meet the man who taught physics what disorder actually is.
What is disorder, actually? Not as a mood, as a number you could compute.
In the 1870s, a physicist in Vienna set out to answer exactly that, and the answer he found is the reason the recurrence paradox has teeth. His name was Ludwig Boltzmann, and he was attempting something most of his colleagues considered not merely difficult, but meaningless: to derive the behavior of heat, a smooth, flowing, everyday thing, from the collisions of atoms, at a time when many of Europe's leading physicists did not believe atoms existed at all. Boltzmann's central insight can be held in one hand. The gas in a box has two kinds of description. There is the microstate, the full list, every molecule's position and velocity, the single point in phase space we met earlier. And there is the macrostate, the handful of numbers you can actually measure: temperature, pressure, volume. Here is the insight. One macrostate corresponds to an astronomical number of microstates. The room you are sitting in feels the same to you whether a particular oxygen molecule is by the window or by the door. Swap any two molecules and the temperature does not flinch. So ask, how many microstates wear the same macroscopic face? Count them, and you have measured something profound. Boltzmann called the count W, and he defined entropy, the disorder the second law talks about, through what may be the most consequential short equation in classical physics. S equals K log W. Spoken in full, entropy equals Boltzmann's constant times the logarithm of the number of microstates. S is the entropy of the macrostate. W is the number of microscopic arrangements that produce it. And K, now called Boltzmann's constant, is the exchange rate that converts pure counting into the units of heat, the same constant that today sits inside the definition of temperature itself. Picture what the equation is saying with a jar of 200 coins. Shake it. There is exactly one arrangement in which every coin lands heads, one microstate. But there are more arrangements with 100 heads and 100 tails than there are atoms in a billion universes, because the 100 heads can be any 100 of the 200 coins. If every arrangement is equally likely, the jar does not slide toward half and half because anything pushes it there. It slides there because that is where nearly all the arrangements live. Entropy is not a force, it is a census. And with that census, the second law transforms. Why does heat flow from hot to cold and never back? Why does the perfume spread and never regather? Boltzmann's answer: because the spread-out arrangements outnumber the gathered ones by factors with trillions of digits, and a system stumbling blindly through its possibilities will, with overwhelming likelihood, stumble into the enormous majority and stay there. In 1872, he sharpened this into a formal result, the H-theorem, which appeared to prove from mechanics alone that a gas's entropy can only climb. Not usually climbs, can only climb. A one-way street built from two-way traffic. I know this stretch has been dense. Two theorems, a space with trillions of axes, and a census of arrangements. So pause on something small. Look at the steam rising off a cup of coffee, or the frost feathering a window. Every one of those everyday sights is the census in action, countless molecules voting for the majority arrangement. You have been watching statistical mechanics your whole life without the name. And if this walk through it is holding your attention tonight, a quiet tap on the subscribe button helps more of these long explorations find the people who want them. Now, because the H-theorem's one-way street is about to meet a theorem that says every street runs in circles. Trouble arrived before Poincaré ever entered the story. In 1876, Boltzmann's own colleague in Vienna, Joseph Loschmidt, posed an objection of devastating simplicity. Every collision between two molecules is reversible. Film it, run the film backward, and the reversed collision obeys the laws of mechanics perfectly. So take your gas after it is spread and smoothed, and reverse every velocity at once. Mechanics must now run the whole history backward. The smooth gas unmixes, regathers, marches straight back to its ordered beginning, entropy falling the entire way. For every history that climbs toward disorder, mechanics contains its mirror twin that descends. How can a one-way law emerge from ingredients with no arrow in them at all? Boltzmann never fully silenced that question. It was still hanging in the air when the mathematician arrived, carrying, of all things, a competition entry about the sky. In 1885, the King of Sweden and Norway, Oscar II, announced a mathematics prize to mark his 60th birthday, with a jury of three of the most formidable mathematicians in Europe: Charles Hermite, Gösta Mittag-Leffler, and Carl Weierstrass. Among the posed challenges stood the oldest open wound in celestial mechanics, the three-body problem: the Sun, the Earth, and the Moon, or any three masses pulling on one another by gravity. Two bodies Newton had solved completely, their orbits close into perfect repeating ellipses. Add a third body, and 2 centuries of the finest minds in Europe had failed to produce a general solution. The deeper question underneath: is the solar system stable? Do the planets circle on schedule without end, or does the clockwork someday come apart? Henri Poincaré, then in his 30s and already regarded as the most penetrating mathematician of his generation, submitted a massive memoir attacking the problem. And in January 1889, the jury declared him the winner, a gold medal and 2,500 kroner. Then came one of the great productive catastrophes in the history of mathematics. As the memoir was being prepared for publication in the journal Acta Mathematica, a young editor named Edvard Fragman kept finding passages he could not follow, and pressed Poincaré to clarify. The clarifications kept failing, and working through Fragman's questions, Poincaré discovered that one of his central claims, a claimed proof of stability, was simply wrong. The published memoir had to be recalled and rewritten, swelling from 158 pages to 251, and in the rewriting, Poincaré confronted what his error had been hiding. orbits of infinite, inexhaustible complexity, tangles so intricate he confessed he could not even attempt to draw them. Modern mathematics calls what he found homoclinic chaos. The first glimpse of chaos theory, sensitive dependence, the impossibility of long-range prediction, entered science as the correction of a prize-winning mistake. And inside that same memoir, published in 1890 in Acta Mathematica Volume 13, sits the theorem this whole night rests on. Poincaré proved that a bounded mechanical system must return arbitrarily close to its initial condition, and return again, without end. Notice the irony, because it is exquisite. The memoir that shattered the dream of perfect prediction, that showed we cannot forecast three gravitating bodies indefinitely, also proved that in the longest run, the system is condemned to repetition. We cannot say what happens next. We can say it will all happen again. Chaos and recurrence, born in the same document, from the same corrected error. Poincaré saw immediately what his theorem meant for Boltzmann's one-way street, and he did not soften it. In 1893 he wrote, "Of the claim that heat can never flow from cold to hot, a sentence with a mathematician's dry cruelty. To see it happen, it will suffice to have a little patience." The H-theorem said entropy can only climb. The recurrence theorem said every climb must someday be unclimbed. One of them had to bend. The man who forced the confrontation was not Poincaré himself, but a young German mathematician named Ernst Zermelo, an assistant in Berlin to Max Planck, and by temperament exactly the wrong person to ignore a contradiction, trained in a school that, as historians put it, accepted no deviations whatever from the second law. In 1896, in the Annalen der Physik, the leading physics journal of the age, Zermelo published a paper with a polite title and a brutal content. The recurrence theorem, he argued, does not merely complicate the mechanical theory of heat, it refutes it. If every mechanical state of a sealed gas must recur, then entropy cannot be a quantity that only climbs. Mechanics guarantees it must someday descend to its starting value. Either the second law is not universal, or heat is not mechanics. You cannot keep both. What do you do when a theorem and a law of nature collide head-on, when the mathematics is airtight and the law has never once failed? Boltzmann's reply, in the same journal the same year, is one of the great documents of scientific combat, and its core move is the one that saved his life's work. He conceded the theorem and reinterpreted the law. Yes, he granted, recurrence is mathematically certain. He noted with some heat, made the same point himself years earlier. But the second law was never an absolute decree. It is a statement of overwhelming probability. Entropy does not always climb. It almost always climbs, because the disordered arrangements outnumber the ordered ones by those factors with trillions of digits. The descent Zermelo demanded is real, and it is certain, and then Boltzmann computed when. For 1 cubic centimeter of ordinary air, a sugar cube of room, holding what he counted as about 1 trillion molecules, the waiting time for a full return is a number whose digits themselves number in the many trillions. Not a number with trillions in it, a number that takes trillions of digits to write down. Stop and try to feel the size of that, because Boltzmann himself built the comparison. Imagine, he wrote, every star you can see through a telescope carries planets, every planet carries humans, and every human lives 1 trillion years. Add up all the seconds in all those lives. That total, every heartbeat of a galaxy spanning humanity, is a number with fewer than 50 digits. The recurrence time for a cubic centimeter of air needs trillions of digits. The gap between those two numbers is not a gap of degree. It is a gap between everything that could ever be experienced and what the mathematics nonetheless guarantees. And then Boltzmann delivered the sentence that settled the argument's tone for the next century. A man who calculates that a fair pair of dice must eventually throw 1,000 ones in a row and then declares the dice loaded because he has never seen it happen. That man, Boltzmann wrote, is Zermelo. The recurrence theorem involves no contradiction with experience, he concluded, since the length of this time makes any attempt to observe it ridiculous. and of the recurrence time itself, he chose an extraordinary word. The number, he wrote, is comfortingly large. Tröstlich groß. Comforting, because a mathematical certainty that can never be witnessed cannot hurt you. There is a legend, told but never documented, that he put it more bluntly to a challenger. You should live that long. The published words are barbed enough. Zermelo did not surrender. In his rejoinder the following year, he made his priorities explicit. As one historian renders it, he preferred to give up the theorem's relevance rather than give up the principle. The second law was, for him, the fixed star, and any mechanics that contradicted it was the thing to abandon. Boltzmann answered once more in December 1896, and buried in that second reply, he planted a seed that will detonate in the final act of tonight. Perhaps, he mused, the universe as a whole sits in equilibrium, dead, smooth, disordered, and what we call our world is a rare local fluctuation, a temporary regathering of order in one corner, the kind of descent his own statistics said must occasionally occur. A universe-sized version of the perfume finding its way back into the bottle. Keep that thought where you can reach it. A century later, it returns wearing a stranger face than Boltzmann could have imagined, and it nearly breaks modern cosmology. What does it mean that the deepest comfort available to 19th century physics was found not in a law forbidding the return, but in a number postponing it past every witness? That the difference between never and beyond all clocks turned out to be a difference no experiment could ever be built to detect. So who won? On the narrow question, Boltzmann. The second law survives as a statistical law, and every physicist alive works within his reading of it. Entropy climbs not because descent is forbidden, but because descent is outnumbered beyond all reckoning. The one-way street is real, and it is made entirely of two-way bricks. The arrow of time itself, on this account, is a fact about counting, not about the laws. But notice what the truce actually signed. Recurrence was not refuted, it was postponed. Both men agreed the return is mathematically mandatory in a sealed, finite system. They disagreed only about whether a certainty beyond all witnessing deserves a place in physics. What does it mean that the deepest argument of 19th century physics ended not with the return cancelled, but with the return scheduled past every clock that will ever tick? There is a personal note here that I keep returning to. Boltzmann spent his career defending the reality of atoms against colleagues who called them fictions, and the fight wore him down in ways his biographers document with sorrow. He did not live to see Jean Perrin's experiments vindicate the atom beyond dispute just a few years after his death. The man who counted the arrangements of the world was, in his own arrangement, singular and unrepeated, within any time that will ever matter. The equation on his monument in Vienna is the one you heard tonight. S equals K log W. But the truce between Boltzmann and Zermelo, elegant as it is, rests on an assumption neither man could check. An assumption so natural you likely did not notice tonight's argument making it. The dice player retort, the census of arrangements, the trillions of digits waiting time. All of it presumes that the wandering point in phase space actually wanders, that given endless time, the system really does explore its whole catalogue of arrangements instead of circling forever in some small, familiar wing. Does it? Does a real physical system visit everything its energy allows? That innocent-sounding question has a name, and it has one of the strangest experimental histories of the 20th century. The place it was finally put to the test was not a laboratory in Vienna. It was a room full of vacuum tubes in the New Mexico desert in the last months of a dying man's career. Does a sealed system, given endless time, actually visit every arrangement its energy allows? Physics has a name for the claim that it does, the ergodic hypothesis. Stated carefully, it says that a system wandering through phase space spends, in the long run, equal time in equal volumes. That the wandering point plays no favorites, that every room in the catalogue eventually gets its visit, and gets it as often as its size deserves. Boltzmann needed something like it for his census argument to work. Counting arrangements only predicts behavior if the system genuinely samples the arrangements. The recurrence theorem, remember, does not need ergodicity. Poincaré's proof used only the sealed walls and the incompressible flow. But everything quantitative about recurrence, how long, how often, how the waiting time depends on what you are waiting for, lives or dies by how the system explores. So, does it explore? Before the experimental answer, there is a piece of mathematics that turns the question razor sharp. And it is worth 1 minute because it is the second equation of the night and the most quietly astonishing. In 1947, the mathematician Mark Kac proved that for an ergodic system, the average waiting time for a return to some set of arrangements equals 1 divided by the measure of that set. Spoken plainly, the mean return time equals 1 over the fraction of the catalogue you are waiting for. That is the whole equation. The return time is the reciprocal of the rarity. If the arrangement you want occupies 1/1,000,000th of the catalogue, you wait, on average, 1,000,000 steps. 1/1,000,000th, 1,000,000,000,000 steps. The rarer the room, the longer the corridor. And the relationship is not vague but exact, a conversion table between rarity and patience. Feel what that equation is saying with a combination lock. A lock with 6 dials of 10 digits has 1,000,000 settings. Spin all 6 dials at random once per second, and on average the lock will pass through the full correct combination once every 1,000,000 seconds, about 11.5 days. Add 4 more dials and the average wait climbs past 3 centuries. Every digit multiplies the corridor 10-fold. Now let the lock be a cubic centimeter of air, where the number of settings has trillions of digits, and Kac's little equation becomes Boltzmann's monstrous waiting time, not as rhetoric, but as division. The perfume regathers, the air huddles in its corner, the moment returns, each at a frequency set precisely by how rare it is. Rare beyond writing means late beyond writing.
There is a detail in Kac's result that rewards a pause. It speaks of averages, and for chaotic systems, the arrivals around that average follow the most patternless schedule imaginable. The same statistics as raindrops on a roof, or clicks in a radiation counter. Returns do not come on a timetable. They come like a bus line with no schedule at all, where knowing a bus just left tells you nothing about the next one. The universe's repetitions, if they happen, are not a clockwork carousel. They are a rain of coincidences, spaced by chance around an average too large to write. The French mathematician Émile Borel, in 1913, gave the rarity half of this picture the image it has worn ever since. Take 1,000,000 monkeys, he wrote, and set them typing 10 hours a day. The chance that a year of their combined random keystrokes reproduces the contents of the world's great libraries is, he computed, absurdly, dismissibly small. And yet, he insisted, that absurd chance is enormously larger than the probability of a visible violation of statistical mechanics. Larger than the odds of the air in a room clumping to one side on its own. Larger than the odds of the lukewarm coffee sorting itself back into hot and cold. Arthur Eddington carried the monkeys into English physics in 1928, and they have typed in every probability lecture since. But keep Borel's actual point, which is sharper than the image. He was not saying prodigies of typing happen. He was saying the everyday steadiness of your room is underwritten by odds so lopsided that a library-writing monkey is, by comparison, a safe bet. Improbable does not mean impossible. It means scheduled beyond reach, which is exactly what Kac's equation turns into arithmetic. I want to pause here because we are 40 minutes in and the argument has been climbing steadily. Look around the room you are in. Every number tonight, the census, the reciprocal rule, the monkeys, is a statement about the room, about the air holding its even spread, the coffee cooling on schedule, the wall staying a wall. The strangeness we are building toward is not somewhere else in the universe. It is the fine print on the most ordinary hour of your life. Hold that,
because the next stop is the moment the fine print was finally put to an experimental test, and the test came back wrong. The test happened, of all places, at Los Alamos in 1953 and 1954 on one of the first electronic computers in existence, a machine called the Maniac, built for weapons calculations and available in the gaps for something stranger. Enrico Fermi, in what would be the last stretch of his career, teamed with the physicist John Pastor and the mathematician Stanislav Ulam to try something no one had ever done: use a computer not to calculate a number, but to run an experiment in pure mechanics, a numerical world watched over time. They built the simplest system that could possibly show the road to disorder, a one-dimensional chain of 64 points connected by springs, like a guitar string rendered as beads, with one decisive twist. The springs were made slightly non-linear, their pull not quite proportional to their stretch. The program that made it run was written by Mary Tsingu, a young mathematician whose name the resulting report omitted for half a century. The work is now, properly, called the Fermi-Pastor-Ulam-Tsingu experiment. What did they expect? Exactly what Boltzmann's census predicts. Pluck the chain in its simplest possible shape, all the energy in the single lowest mode, one grand, smooth arc, and the nonlinearity should let the modes trade energy. The trades should scramble, and the energy should spread until every mode holds an equal share. Order into disorder. The whole arc of the second law miniaturized. The beaded string was supposed to forget its beginning. The machine ran. The energy began to spread, just as expected, into the second mode, the third, the fourth, and then it stopped spreading. The flow hesitated, turned, and began to regather. After a few hundred oscillations of watching, the energy came flooding back into the original mode. Not all of it, but some 97%, and the string stood, for a moment, in nearly the exact grand arc it had been plucked into. Then the cycle began again. The system was not forgetting its beginning, it was rehearsing it. Fermi is reported to have called the result a little discovery, with the dry understatement of a man who suspected otherwise. He died in November 1954, and the report, one of the most consequential documents never published in a journal, circulated from Los Alamos in 1955 after his death. It is widely credited with founding computational physics itself, the first time a computer served as a laboratory, and the first time the laboratory said no to the second law's most natural expectation. Here was a sealed, finite mechanical system, bounded, volume-preserving, everything Poincaré requires, and instead of wandering off into its enormous catalogue of disordered arrangements, it circled. Recurrence, not in trillions of digits of waiting, but in an afternoon of machine time. Which forces the question the whole field then had to face. If the census argument is right, if disorder outnumbers order beyond all reckoning, how does a system this simple refuse the odds? What was holding the string back from its own phase space? The answer had been announced, with almost eerie timing, 1 year earlier, by a mathematician on the other side of the Iron Curtain. In 1954, at the International Congress of Mathematicians in Amsterdam, Andrei Kolmogorov sketched a theorem about what happens to an orderly mechanical system when you disturb it slightly. Take a system whose motions are perfectly regular, planets on their clockwork ellipses, the beads on a linear string, anything whose phase space paths wind forever around smooth, nested surfaces, like threads wound on a family of nested rings. Now add a small nonlinear disturbance, a tug, a coupling, an imperfection. The natural guess, the guess behind the ergodic hypothesis, is that any real disturbance shatters the clockwork and sets the system wandering everywhere its energy allows. Kolmogorov announced, no. For small disturbances, most of the nested rings survive, deformed, warped, but unbroken, and a path caught on a surviving ring circles it forever, sealed away from the rest of phase space, never to explore it. His sketch was made rigorous over the following decade by Jürgen Moser in 1962 and by Vladimir Arnold in 1963, and the result now bears their three initials, the KAM theorem for Kolmogorov, Arnold, and Moser.
Hold the picture the theorem paints, because it overturns the neat story every popular account of entropy tells. Phase space, for a gently disturbed system, is not an open ocean where every current eventually mixes with every other. It is an archipelago, islands of surviving order, the unbroken rings where motion stays regular and repeats, threaded through a sea of chaos where paths do wander and mix. Order and chaos are not sequential eras, one giving way to the other. They coexist at the same instant, in the same system, interleaved at every scale, and which future a path receives depends only on where it starts. The Fermi-Pastor-Ulam-Tsingou string, plucked in its lowest mode, had started on an island, close enough to the orderly linear system that the surviving structure carried its energy in closed circuits, back to the beginning again and again. The ergodic hypothesis as a universal principle is false. Some systems explore everything. Others are trapped in gilded rooms of their own regularity, repeating not because they have exhausted the catalogue, but because they can never reach it. Notice what this does to the recurrence story, because it cuts both ways, and the cut is instructive. It weakens one thing, the clean claim that a system visits everything, which Cat's equation quietly leaned on. Waiting times, it turns out, depend on the terrain. A system on an island returns fast and forever. A system in the chaotic sea returns on Boltzmann's unwritable schedule. And a real system is a mixture of both. But it strengthens the deeper thing. Recurrence itself never needed ergodicity. On the islands, return is not merely certain but frequent. The trap is a loop. In the sea, return is Poincaré's, rare and patient but mandatory. Everywhere you start, in a sealed finite system, the road bends home. The only question the 20th century added is how long the road is. And for that question, the difference between the islands and the sea is the difference between an afternoon on a computer in New Mexico and a number with trillions of digits. What does it mean that the first time humanity built a world in a machine and let it run, the world's first spontaneous act was to return to its beginning? And there is a warning buried in the FPUT result, one we will need in the final act, so I will plant it now and ask you to keep it. Later, much more powerful computations returned to the beaded string and ran it not for hundreds of oscillations, but for millions. The recurrences, it turns out, are not the whole story. Watched long enough, the string's rehearsals slowly blur. Energy leaks, imperceptibly at first, out of the circulating pattern. And over spans vastly longer than the original experiment could see, the system does creep toward the even-sharing Fermi expected on day one. The first glimpse said the second law had failed. The long view said it had only been delayed. Hold on to that shape, the early result that looks like a law breaking, and the longer view that quietly restores it. Because tonight's final question, the one about the universe itself, will come down to which of those two moments we are living in. So the classical books close on a remarkable consensus. A sealed, finite, mechanical world repeats, by theorem in the chaotic sea, by construction on the islands of order, on timescales running from afternoons to numbers beyond writing. Poincaré proved it, Boltzmann priced it, Katz scheduled it, and a computer in the desert caught it happening. But every word of that consensus describes a classical world. Molecules as tiny billiard balls, states as points, motion as a line through phase space. And the actual furniture of the universe obeys none of those pictures. Atoms are quantum objects, their states are waves, their properties come in discrete steps, their futures are probabilities. Surely, you might think, all this 19th century clockwork dissolves in the quantum world's fog, that uncertainty of all things would break the appointment. It is a reasonable expectation. It is also, remarkably, backwards. Quantum mechanics does not weaken the recurrence theorem. It makes it stricter, more exact, and, for the first time, applicable to you. Why would quantum mechanics,
the physics of uncertainty, of fuzziness, of probability, make repetition stricter rather than looser? The answer hides in a property of quantum systems that sounds technical and turns out to be everything. Confinement makes quantum states discrete. Trap a particle in a box and it cannot carry just any energy. It is allowed a ladder of specific energies, a lowest rung, a next rung, and so on, with nothing permitted in between. This is the very fact that gives quantum mechanics its name. Confined systems come in quanta, in steps. And a bounded system whose possibilities come in steps is a system with a countable catalogue. The classical picture needed clever arguments about volumes in phase space to make its catalogue effectively finite. The quantum picture hands you discreteness at the door. What does that discreteness do to the passage of time? Something with no classical equivalent. The state of a sealed quantum system is a sum of its energy rungs, each rung turning at its own steady rate, like a set of clock hands of different speeds, and the system's entire future is just those hands turning. Nothing scrambles, nothing forgets. The hands simply rotate, each at its own frequency without end. And in 1957, two Italian physicists, Paolo Bocchieri and Adriano Loinger, published in the Physical Review the theorem this fact forces. Any quantum system with a discrete energy spectrum must return arbitrarily close to its initial state and return again without end. Written as mathematics, the statement is almost insolently short. There exists a time t at which the distance between the state then and the state now, written as the norm of psi at time t minus psi at 0, is smaller than any epsilon you name. Psi is the system's complete quantum state, the full description physics allows. Epsilon is your standard of sameness, and you may set it as unforgivingly as you please. The theorem does not negotiate. Name your epsilon, and a time t exists that beats it. Picture the clock hands to feel why. Two hands turning at different steady rates drift apart, sweep the whole face, and eventually pass within a hair of realignment. You have watched a clock's minute and hour hands do exactly this. Add a third hand, a hundredth, a trillionth, each with its own rate, and alignment becomes fantastically rarer. But the logic never breaks. Steady rotations on a closed dial must come back within any tolerance you set, given time. A quantum state is that clock, with one hand per energy rung. Its return is not an accident the theorem hopes for. It is what turning in circles means. Now hold the quantum theorem next to the classical one, because the upgrade is the point. Poincaré's theorem promised a return of position. The wandering point comes back near where it began, while chaos scrambles everything along the way. The Bocchieri-Loinger theorem promises the return of the entire state vector, not a summary, not a coarse resemblance, but the complete physical description of the system. Every correlation, every phase, everything the universe knows about it, back to within your chosen epsilon. And where the classical result had to survive the archipelago, islands here, chaotic seas there, waiting times hostage to the terrain, the quantum result knows no terrain at all. Discrete spectrum in, recurrence out. No exceptions for chaos, no carve-outs for complexity. The philosopher of physics David Wallace, who in 2015 unified the classical and quantum results into a single account, put the shared engine in one sentence. A system with a finite state space only has so many places to go. Only so many places to go. That phrase is the entire night compressed. And notice who it now applies to. You are a physical system, a warm, complicated, gloriously messy one, but a quantum system all the same, some 10 to the 28th atoms, every one of them obeying the same mechanics as the particle in the box. Seal any such system in a finite region with finite energy, and the theorem attaches. The arrangement of matter that is you, this room, this exact moment of hearing, if the container is closed and the catalogue finite, That state must, by mathematics no one disputes, come back within any epsilon and keep coming back. The 19th century proved the perfume returns to the bottle. The 20th proved the listener returns to the chair. Before I continue, stop and consider what has just been claimed, because it deserves a moment of stillness rather than another fact. Take stock of the chain, link by link, and test it yourself. Confined quantum systems have discrete states, that is measured in every atom in every laboratory on Earth. Discrete states turning steadily must realign, that is the clock hand argument, and you can check its logic in your head. Realignment is return, that is the theorem, 3 lines in a 1957 journal. Which link would you break? Because if none of them breaks, then the conclusion is already inside you, the way the statue is inside the marble. Sealed and finite means repeating. Every remaining hour of tonight is really about one thing, whether the universe, examined honestly, supplies the words sealed and finite. The mathematics has done all it can. From here forward, the load shifts to the telescopes. So everything now hangs on 2 words, sealed and finite. And on a question we have been circling since the first minute. How long? For a cubic centimeter of air, Boltzmann said trillions of digits. What is the honest number for a universe? In 1994, a physicist sat down to compute it, and the answer became famous. His name is Don Page, a theorist known for work with Stephen Hawking on black holes, and in a paper about information loss, he worked out the quantum recurrence time for the largest bounded system he could defensibly write down. Take a mass equal to everything the universe holds. Let it settle into the most information-dense object physics allows, a black hole, and let its radiation fill a sealed box. Count the states. Apply the theorem. Page's formula for the waiting time is a double exponential, e raised to the power of e raised to 4 pi m squared, with the mass measured in the natural units of quantum gravity. Put the universe's numbers in, and what comes out is a tower. 10 raised to 10 raised to 10 raised to 10 raised to 2.08. 4 stories of exponents. It has been called the longest finite time ever computed in a physics paper. I need you to sit with how large that is, and the honest truth is that you cannot, no one can. But there is one property of the number that lets you touch its edge. Ask, is that time in seconds? In years? In ages of the universe? And the answer is, it does not matter. Convert seconds to years and you divide by about 30 million, an adjustment of 8 digits. But the number's top story is itself a 1 followed by 120 digits worth of structure. An 8-digit correction drowns in it without leaving a ripple. Page's tower is the same number in nanoseconds and in lifetimes of the cosmos. A quantity so large it erases the difference between a blink and an age has, in the plainest sense, left every human scale behind, and it is still finite. That is the appointment's honest schedule. This is the part that stays with me, I will admit. Not that the return happens, the theorem settled that, but that the waiting time is a number you can write on one line with 4 tens, and it swallows all clocks whole. For calibration, here is the whole ladder of the far future, each rung unimaginable from the rung below. The universe today is about 13.8 billion years old, some 10 to the 17.5 seconds. The last black holes are expected to evaporate by around 10 to the 100 years. The horizon, usually called heat death, orders final flattening. Page's recurrence tower stands above that the way that number stands above a second. No, incomparably beyond that, because comparison itself fails between exponent stories. And Page computed one rung more. For a universe inflated to the vastness some cosmological models suggest, the tower gains a 5th story, 10 to the 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 1.1 in years. Though by now you understand why the unit is a joke the number tells at our expense. Somewhere past all clocks, the mathematics calmly schedules the reunion.
I know these towers are vertiginous, so let me put solid ground underfoot for a breath. Nothing in your day, your decade, or your species story is touched by any of this. That is precisely what the towers mean. The coffee still cools, the egg stays broken. Every practical promise of the second law holds to the last digit any instrument will ever check. What tonight changes is not your calendar, it is the fine print under the word never, the discovery that physics, read carefully, does not actually stock that word, and stocks instead a number with 4 stories of tens. Whether even that number survives contact with the real sky is the final act's question, and everything now depends on it. But before the sky, one more counting argument, because the same arithmetic that schedules repetition in time turns out to predict something stranger in space, and it is the single most quoted number in this entire subject. The bound that makes the counting legitimate came from Jacob Bekenstein, who proved in 1981 that a finite region with finite energy can hold only a finite amount of information, a hard ceiling, set by nothing more than the region's size and its energy content. No infinite subtlety hides in a bounded box. The catalogue of physically distinguishable states in any finite volume is a finite catalogue, full stop. In 2003, the cosmologist Max Tegmark did the counting for the largest box that matters, our entire observable universe, the sphere some 93 billion light-years across that light has had time to show us. A volume like ours, at temperatures no hotter than 100 million degrees, holds at most about 10 to the 118 protons. Each can crudely be present or absent in a given slot, 2 to the 10 to the 118 arrangements, which is, to the precision such numbers deserve, 10 to the 10 to the 118. A 1 followed by 10 to the 118 digits. That is the complete catalogue of ways a universe-sized room can be furnished. Now run Kak's logic sideways. If space extends far beyond our horizon, and every measurement of its flatness suggests it extends enormously farther, perhaps without limit, and if matter out there is dealt from the same catalogue by the same physics, then the arrangements must repeat across distance for exactly the reason they repeat across time. A finite deck dealt endlessly duplicates. Tegmark computed the average spacing, the nearest exact copy of you, atom for atom, memory for memory, a person who has lived your life to this second and is saying your word with your voice, should sit about 10 to the 10 to the 29 meters away. Not a similar person, the same arrangement elsewhere in the deal. Farther out, around 10 to the 10 to the 92 meters, the duplication widens to a sphere 100 light-years across, a copy of everything you could perceive for the next century, perfect to the last photon. And at roughly 10 to the 10 to the 115 meters, an entire duplicate observable universe, furnished identically down to the last proton slot. The recurrence theorem said, wait, and this moment returns. The counting says, travel, and this moment is already there. Repetition in time, repetition in space, 2 shadows of the same fact. The catalogue is finite, and the universe is larger than its catalogue. What does it mean that the word you spoke at the start of tonight may not need to wait for its return? That arithmetic this simple, applied to a sky this large, concludes the word is being spoken now, by you, somewhere past a horizon no light will ever cross. Before you object, notice that you already know the objections, because we built them together. Does that spatial counting not assume the deal is random and even, a kind of ergodicity of space? It does, and Tegmark says so plainly. The estimate leans on matter out there being shuffled from the same deck at the same odds, an assumption cousin to the one KAM taught us to distrust. Does the temporal theorem not assume the walls are sealed? It does. Poincaré's first condition, the one I asked you to keep a hand on an hour ago. Every tower tonight, Page's and Tegmark's alike, stands on the same 2-word foundation, sealed and finite. And here is the turn the whole night has been building toward. In 1998, 2 teams of astronomers, measuring the light of dying stars halfway across the observable universe, discovered what the sky itself has to say about those 2 words. What they found took the foundation out from under every calculation you have just heard, or proved it forever, depending on a question that remains, tonight, genuinely open. That discovery is the final act, and nothing before it survives unchanged. What did the astronomers actually find in 1998? Two rival teams, one led by Saul Perlmutter, the other with Adam-Riess doing the decisive analysis, had spent years timing the light of Type 1a supernovae, dying white dwarf stars that detonate with such uniform brightness that they serve as standard candles across billions of light years. The plan was to measure how much the universe's expansion has been slowing, braked by the gravity of everything it contains. The distant supernovae came back dimmer than any braking scenario allowed. Dimmer means farther. Farther means the expansion has not been slowing at all. It has been speeding up. Both teams, fighting their own disbelief, converged on the same conclusion within months of each other. For the last several billion years, space itself has been stretching faster and faster, pushed by something with negative pressure woven into empty space. Physics named the something dark energy, and its simplest candidate, the one every measurement since has remained consistent with, is the cosmological constant, a fixed energy in every cubic meter of vacuum, unchanging, undiluting, written into the fabric. Here is what acceleration seems to say to everything you have heard tonight, and why the first reading of it was an obituary. Poincaré's theorem needs walls, a bounded system the wanderer cannot leave. An accelerating universe has no walls. It manufactures new space, without limit, without end, faster and faster. Galaxies beyond our neighborhood are carried apart at ever-growing rates. The room does not merely grow, its growth compounds. A catalogue that grows without bound is no catalogue at all. The deck gains fresh cards faster than any shuffle could exhaust the old ones, and the pigeonhole argument, which was the entire engine of return, quietly dies. On this reading, the recurrence theorem remains perfect mathematics and simply stops describing our universe. The moment passes, the arrangement disperses into an expansion that never stops diluting it, and never, the word physics did not stock, comes back into stock.
That was the first reading. The second reading is the reason this video exists, and it emerged from the same equations within a few years, in one of the strangest reversals in modern cosmology. A universe with a positive cosmological constant does not just accelerate, it matures into a very particular space-time, one that Willem de Sitter had written down as a solution of Einstein's equations back in 1917, decades before anyone needed it. De Sitter space, the geometry of pure exponential expansion. And de Sitter space has a feature no other endpoint has. Because distant regions are carried away faster than light can close the gap, every observer becomes surrounded by a horizon, a boundary, roughly 16 billion light-years out for our value of the constant, past which no signal can ever again arrive. Not because light slows, but because the space in between breeds faster than light crosses it. The accelerating universe, the very thing that seemed to abolish all walls, builds a wall around every observer, and seals it forever. Pause on how strange a wall that is, because nothing in ordinary experience prepares you for it. It is not a place. Fly toward it and it recedes. Your neighbor 30 billion light-years away has their own horizon, centered on them, overlapping yours the way two lamplit circles overlap on a dark street. It is a wall made not of material but of arithmetic, the point at which the growth of the road outruns every traveler on it. Picture a moving walkway, miles long, whose speed increases with distance from you. Nearby, you can walk against it. Farther out, you break even. Beyond a certain line, no runner, no signal, no light will ever make headway toward you again, though nothing anywhere moves faster than light through its own local space. Everything beyond that line is finished happening, as far as you are concerned, not destroyed, just permanently elsewhere. And by the same token, everything inside the line is, in the only sense that ever matters for physics, your entire universe. A sphere of finite radius, finite energy, finite content, from which nothing escapes and into which, eventually, nothing new arrives. What does it mean that the same acceleration that isolates every observer behind a private wall is also the only mechanism on offer that could make a universe finite enough to obey Poincaré. Does a horizon count as a wall in the sense the theorem needs? That question has an exact answer, and it comes from black hole physics. Work by Bekenstein and Hawking in the 1970s established that horizons carry entropy. A horizon is not just a boundary but a ledger, and its area measures the information it hides. Gary Gibbons and Hawking showed the same holds for the de Sitter horizon. It has a temperature and it has an entropy, given by the same law that governs black holes. The entropy equals the horizon area divided by 4 in the natural units of quantum gravity, and for a cosmological constant, that works out to 3 pi divided by lambda. S equals A over 4. S equals 3 pi over lambda. 2 ways of writing the fourth and final equation of the night. A is the horizon's area, the surface of the sphere past which nothing returns. Lambda is the cosmological constant, the strength of the vacuum's push. And S, the entropy, counts the states. The smaller the constant, the larger the horizon, the bigger the ledger. Feel what the equation is doing. It takes the size of the push that empties the universe, inverts it, and hands back the size of the library that universe can ever contain. The force of endless dilution and the count of everything possible, locked into one line as reciprocals of each other. Put in the measured value of the cosmological constant, and the entropy of our horizon comes out at about 10 to the 122. The number of distinguishable quantum states available inside the horizon is then E raised to that entropy, e to the 10 to the 122 states, enormous beyond every comparison tonight except the ones that matter, and finite. There is the trap, sprung. A sealed region, the horizon guarantees it. A finite catalogue, the entropy counts it. Those are Poincaré's 2 conditions, delivered not by assumption but by the accelerating sky itself. The acceleration everyone took for recurrence's executioner turns out, if the constant is truly constant, to be the very thing that furnishes recurrence its walls and its ledger. The recurrence time that follows is e to the 10 to the 122, a tower more modest than pages, and it hardly matters. Seconds, years, ages of the universe, the same number. In a universe whose vacuum never changes, every arrangement inside the horizon, this room, this sentence, this listener, sits in a finite library that endless time is required to reread. In 2002, 3 physicists faced this squarely in a paper whose title tells you they understood what they were holding. Disturbing Implications of a Cosmological Constant by Lisa Dyson, Matthew Kleban, and Leonard Susskind. Susskind being one of the founders of string theory and among the most influential theorists alive. They are the authors I promised an hour ago, the ones who walk with full mathematical control through what the sealed horizon permits. Weight e to the 10 to the 122, and the air in your room gathers itself into a corner smaller than a sugar cube. Because that arrangement is in the library, and the library must be reread. Wait longer, and whole planets, whole observers, reassemble out of thermal fluctuation. Their own abstract does not flinch, and I will quote it exactly. These assumptions, they wrote, inevitably lead to very deep paradoxes, which seem to require major revisions of our usual assumptions. Read that sentence twice. The authors are not popularizers reaching for drama. They are reporting that the 2 best established facts of their field, quantum mechanics and the accelerating vacuum, jointly generate conclusions they themselves cannot accept, and that something in the foundations must give. Juan Maldacena, whose discovery of the anti-de Sitter correspondence underlies half of modern theoretical physics, had shown the year before that in the pristine mathematical laboratory of anti-de Sitter space, recurrences of exactly this kind genuinely occur. Correlations that decay for ages and then, mandated by finiteness, return. The mathematics holds together. That is precisely the problem. What does it mean that the two most successful frameworks in the history of measurement, quantum mechanics, tested to 12 decimal places, and the accelerating vacuum, confirmed by every survey since the supernovae, multiply together into a future their own authors file under paradox? Let the machinery of that future be concrete for a moment, because the pricing of fluctuations is the hinge everything ahead swings on. A horizon with a temperature is a horizon that jitters. Gibbons and Hawking established the temperature, and a warm surface enclosing a sealed room means the room can never settle into perfect stillness. It simmers, faintly, without end. Most of the simmering is nothing, a few particles too few to notice, assembled and gone. But the pricing follows the reciprocal rule you already own. An arrangement's waiting time is set by its rarity. Cax's division, now wearing thermodynamic clothes. The cost of a fluctuation grows exponentially with the amount of order it must assemble, entropy paid down like a premium. An actuary would recognize the table instantly. Small claims constantly, large claims rarely, and the schedule of rare events set not by weather, but by how big. A pair of particles, cheap and ceaseless. A snowflake's worth of structure, dearer by an exponential factor. A star, an ocean, an ordered universe. Premiums whose digits themselves need towers. Given a sealed room and endless time, the table does not merely permit the large claims, it guarantees every one of them, on schedule, at the stated price. And the paradox has a face, one you were promised in the first hour. Boltzmann's second reply to Zermelo, December 1896. The seed I asked you to keep. Perhaps, he mused, our ordered world is a rare fluctuation in a dead universe, a local regathering of the kind his statistics guarantees. Now run his idea through the de Sitter library. Fluctuations come at a price set by their size, the reciprocal rule again, rarer meaning later, and the price is exponential in how much order you demand. A whole ordered universe like ours, 13 billion years deep and 90 billion light-years wide, is an extravagance of order. A fluctuation so vast its waiting time makes even the towers of tonight look hasty. But a single brain, one warm object the size of your 2 fists, complete with your memories of this video, your certainty of a past that never happened, floating alone in the dark and dissolving moments later. The per-instant odds are around e to the minus 10 to the 66, beyond negligible in any human span. Yet the sealed de Sitter future offers not a human span, but endless time. And against endless time, every finite improbability cashes out, again and again, without limit. Count the 2 kinds of observer the theory then predicts, complete universes and lone momentary brains. The brains outnumber the universes, not by a little, but overwhelmingly, because a small fluctuation is exponentially cheaper than a large one. Physics literature calls these Boltzmann brains, in half-apologetic honor of the man whose stray idea they weaponize. Follow the logic one step further, to where it becomes vertigo. If the theory is right, then among all observers holding exactly your memories, at this exact apparent moment, the overwhelming majority are not people with histories. They are brief fluctuations equipped with false memories of one. Statistics would then instruct you, calmly, by the same reasoning that price is insurance, to conclude you are most likely one of them, and that this room, this video, and every year you remember assembled themselves an instant ago and will dissolve before the sentence ends. What do physicists do with a conclusion like that? Not what you might fear. Nobody spirals. The sentence, you notice, has not dissolved. Instead, the field runs the argument in reverse, and this is the move to remember for the final weighing. Any theory that predicts its own observers are overwhelmingly deluded has destroyed its own credibility. If you cannot trust your memories, you cannot trust the observations that support the theory, and the theory saws off the branch it sits on. A Boltzmann brain-dominated cosmology is therefore treated not as a revelation, but as a failed prediction. a reductio, evidence that some assumption feeding it must be wrong. The brains are not a discovery about you. They are a smoke alarm going off inside the mathematics of the sealed, finite, endlessly repeating universe. Take a breath with me, because this is the last landing before the summit. Nothing abstract is at stake anymore. Count what is on the table. If the horizon is a true wall and the library truly finite, then the recurrence theorem operates at cosmic scale. Your moment returns, your word is respoken, and, as the unwelcome bonus, deluded copies of your mind vastly outnumber you. If instead something breaks the wall or opens the library, all of it, the returns, the copies, the towers, evaporates into an expansion that never looks back. Two futures, mutually exclusive, both written by physicists of the first rank from the same observations. This is where the night has to earn its title. One last uncomfortable question decides everything, and it is the quietest assumption of the evening, the one hiding inside the phrase I have repeated since the first minute. Sealed by what exactly? Finite, says who? It is time to audit the walls. An hour and a half ago, I asked you to keep a hand on one word in Poincaré's theorem. Bounded, sealed, closed. Every tower this night has built, Boltzmann's trillions of digits, Page's 4 stories of tens, the De Sitter library and its rereading, stands on that single foundation. And it is time to do what physics always does at the end. Return to the assumptions and press on each one until something moves. 3 premises held up the theorem. The laws must run reversibly, and quantum mechanics, evolving every sealed state with perfect reversibility, honors that premise more exactly than the classical mechanics it replaced. The flow must preserve the catalogue's measure, and the quantum version of that, unitarity, is among the most tested statements in science. Reversible, yes. Measure-preserving, yes. Bounded, and here, at the last premise, the whole night narrows to a point. Because the answer turns out to depend on a single number astronomers are measuring right now, and on one question about quantum theory that nobody has settled.
Take the number first. Everything the De Sitter trap requires, the permanent horizon, the fixed ledger of 10 to the 122, the sealed library, follows only if the cosmological constant is actually constant. If the dark energy is a property of the vacuum itself, permanently identical in every cubic meter that expansion breeds. Cosmologists parameterize the question with a number called W, the ratio of dark energy's pressure to its density. A true constant means W equals -1, exactly, forever. And every measurement to date, supernovae, the microwave background, the clustering of galaxies, comes back consistent with -1, to within a few percent. But consistent with is not proof of, and the alternatives have names and champions. If the dark energy is instead dynamical, a field that evolves, thins, or decays, the family of models called quintessence, then the horizon is not a permanent wall but a temporary tideline. Cosmologists including Catherine Fries have built explicit models of evolving dark energy that keep this door open. A dynamical dark energy could relax, the horizon could recede or dissolve, the library could grow without bound, and Poincaré's premise fails not by a little but completely, taking every recurrence with it. Here is a sentence worth the whole evening. Whether the moment you are living returns, or is lost once and for all, currently hinges on whether one measured number equals -1 exactly, or merely almost. Now the audit proper. 4 resolutions of tonight's questions stand in the published literature, each carried by physicists of the first rank. The final act of this channel's work is to weigh them, on the evidence, one at a time. The first position says, the recurrence is real. Take the observations at face value, the constant looks constant, and take the horizon's entropy seriously, and the conclusion follows like a proof. Sealed patch, finite library, mandatory rereading. This is Dyson, Kleban, and Suskind's setup, and its strength is that every ingredient is standard physics. Measured acceleration,
established horizon thermodynamics, the recurrence theorem itself. Its weakness is what its own authors did with it. They titled the result disturbing, derived the deep paradoxes, and concluded that the assumptions, their assumptions, must be revised. And the sharpest instrument against it is the one you have already seen, the Boltzmann-brains census. A sealed, endlessly rereading library predicts deluded observers outnumbering real ones without limit, and a theory whose typical observer cannot trust the theory has, by the field's own working standard, failed a prediction. Where does that leave the first position? Not refuted, nothing tonight is refuted, but standing, by its author's own account, as a paradox demanding revision rather than a description commanding belief.
The second position says, the expansion wins and the moment never returns. This is the mainstream center of gravity, and it was argued with numbers before the paradox papers even landed. In 2000, in the Astrophysical Journal, Lawrence Krauss and Glenn Starkman published a calculation with a title of characteristic bluntness: Life, the Universe, and Nothing, asking what an accelerating universe leaves, in the long run, for anyone in it. Their findings are a systematic closing of doors. The total information any civilization can ever gather in an accelerating universe is finite, not for lack of trying, but because acceleration carries the sources of information over the horizon faster than they can be read. By around 100 billion years, every galaxy outside our gravitationally bound neighborhood will be redshifted past 5,000, stretched, dimmed, effectively erased from the sky. By 10 trillion years, the redshift reaches 10 to the 53, a stretching so extreme that the universe beyond our neighborhood becomes, in their description, truly invisible. Even the fact that space is expanding will no longer be measurable to anyone then looking. Energy available for thought itself runs out. Their calculation allows organized activity to persist for something beyond 10 to the 50 years, and then the books close. On this accounting, the universe is not a sealed room, but an open drain. The phase space available to what remains grows without bound, matter dilutes forever, and the premise of the recurrence theorem is not approximately violated, but violated absolutely. Frank Tipler had, in earlier work within general relativity, proved the complementary theorem directly. In an open, ever-expanding universe, recurrence cannot occur. No trajectory returns, and the observations, on this reading, favor exactly such a universe. The strength of this position is that it asks for nothing exotic. One measured acceleration, extrapolated. Its vulnerability is the same extrapolation. It assumes the constant stays constant in its own way, forever diluting, never relaxing, and it must hold that assumption across spans of time in which, as this channel has learned repeatedly, first extrapolations have a way of being humbled. The third position is the strangest and the newest, and it dissolves the question rather than answering it. In 2015, Kimberly Boddy, Sean Carroll, and Jason Pollack published an argument that the entire fluctuation picture, the regathering air, the reassembling moments, the lone brains, rests on a misreading of quantum mechanics in de Sitter space. A quantum system fluctuates, they argue, only in the sense that measurements of it scatter. Left unmeasured, unobserved, undisturbed, a system in its stationary state simply sits there. And the late de Sitter universe is exactly that, a closed system settling into its stationary vacuum, with nothing outside to measure it. Carroll compressed the claim into one sentence. In de Sitter space, everything is in equilibrium, and, he argues, in a true stationary equilibrium, nothing happens. No fluctuation events, no air in the corner, no Boltzmann brains. Their paper's title is, literally, Why Boltzmann Brains Don't Fluctuate into Existence from the de Sitter Vacuum. And no recurrences. The clock hands of the earlier theorem require a discrete spectrum, a finite-dimensional space of states, and if the true quantum description of the de Sitter patch is infinite-dimensional, the recurrence theorem's premise fails at the quantum root rather than at the cosmological wall. Is that the resolution then, the whole night dissolved by a stationary vacuum? Not yet,
and the reason is instructive. The argument is contested at exactly its load-bearing joint. Whether an unmeasured stationary state truly contains no fluctuating observers depends on what counts as a fluctuation and on the interpretation of quantum mechanics itself. And David Wallace, the same philosopher of physics who unified the recurrence theorems, is on record, through colleagues' published correspondence, disagreeing that stationarity precludes the brains. Two of the field's most careful thinkers, reading the same equations, reaching opposite verdicts about whether anything ever happens again in the far future. That is not a settled answer. That is a live wound in the foundations. And the fourth position questions whether the question was ever well posed. The inflationary models that best explain our universe's smoothness tend not to stop cleanly. In most versions, inflation never everywhere ends. Somewhere it always continues, spawning pocket universes beyond counting. In 2011, Alan Guth, inflation's original architect, and Vitaly Vanchurin showed that in such a space-time, with infinitely many pockets and infinitely many copies of every finite history, the innocent phrase, "how often," simply breaks. To say a configuration recurs rarely or commonly, you must take a ratio of infinities, and the answer depends entirely on how you slice the infinite spacetime into samples. Different slicings, called measures, give flatly contradictory probabilities, and no principle yet chooses among them. Their paper walks into outright paradoxes of probability on this road. On this view, asking whether your moment recurs in the full multiverse is like asking what fraction of the whole numbers are even, and also larger than every number you will ever name. The words pass, and the mathematics beneath them refuses to assign the question a value. The strength of this position is its honesty about a real, unsolved technical problem. The measure problem is acknowledged across the field as foundational and open. Its weakness, as a resolution of tonight, is that it resolves nothing. It tells us the tools break, not what is true. Before the weighing, two objections deserve to be spoken aloud, because if you have followed this far, you are almost certainly holding at least one of them. The first, does heat death not settle this on its own? If the universe runs down into featureless equilibrium by 10 to the 100 years, is the story not simply over, nothing left to recur? It sounds decisive, and it is exactly backwards. Heat death is a macro state, the smooth, disordered, overwhelmingly probable wing of the library where the wandering point spends nearly all its time. The recurrence theorem operates underneath that description, at the level of microstates, and it is completely indifferent to how featureless the room looks from outside. Boltzmann said it first, in that December 1896 reply. The dead sea of equilibrium is precisely the thing his statistics allows to regather, locally, rarely, on the reciprocal schedule. Heat death, in a sealed and finite universe, is not the end of events. It is the waiting room where the rare events are priced. Equilibrium cancels recurrence only if something deeper, an open drain or a truly stationary vacuum, cancels the fluctuations themselves, which is exactly why the second and third positions had to argue for those cancellations rather than simply pointing at the cold. The second objection, surely quantum uncertainty blurs all of this. If states can never be pinned down exactly, what could an exact return even mean? But you have already seen the answer, and it is the night's quiet surprise in reverse. The quantum theorem is stronger than the classical one, not weaker. The Bocchieri-Loinger result is a statement about the full quantum state, uncertainty included. Psi returns to within any epsilon, fuzz and all, because the fuzz is part of the state, and the state is what recurs. Uncertainty does not dissolve the appointment. It is on the guest list. What does it mean that every common sense escape from the recurrence? The universe runs down, the quantum world is too blurry to repeat. Turns out, on inspection, to feed the theorem rather than starve it, so that the only genuine exits run through the sky's acceleration or the vacuum's stillness. Four positions, then, on the table where the night began. The library is sealed and the word returns, held as a paradox by its own authors. The drain is open and the word is lost. The mainstream lean, priced in redshifts and photon counts. The vacuum is still, and nothing was ever going to happen. New, elegant, and disputed at its core by the theorem's own modern custodian. The question outruns our mathematics, true as far as it goes, and going nowhere. What should a careful mind do with a table like that? Exactly what you watched a computer in the desert teach us to do. Remember the beaded string. The first 100 oscillations announced that disorder had failed and return had won. The longer view showed the return slowly leaking away into the equilibrium Fermi expected all along. First frames mislead. And notice which position tonight's evidence most resembles when the frame is widened. Every path to a literal cosmic return demands a stack of exacting conditions. A constant exactly constant, a Hilbert space exactly finite, a fluctuation picture exactly literal, while every alternative needs only one of those conditions to fail. The recurrence to happen must win every coin flip. Oblivion needs one. Before the verdict, one question remains that we have been walking past all night, and it may be the deepest one on the table. Suppose the sealed library picture is right. Suppose the constant is exactly constant, the states are exactly finite, and the fluctuation picture is exactly literal. Every condition met, every coin flip won, the recurrence real. Could anyone, anywhere, ever know? Could the return, when it comes, be witnessed, recorded, confirmed, even in principle? Walk through what a witness would require. To confirm a return, someone must compare this arrangement now against the record of the arrangement then. The comparison needs three things: an observer who persists, a record that survives, and a memory that connects them. Take them in order. The observer. Every calculation of the far future agrees that organized, thinking structures have a deadline. Stars gutter out over trillions of years. The last black holes evaporate by around 10 to the 100 years. Krauss and Starkman's accounting caps the energy available for thought itself. Organized activity beyond about 10 to the 50 years faces an energy famine with no exemptions. Page's tower does not begin to matter until every possible watcher has been gone for spans that make the watcher's whole existence a rounding error on a rounding error. Nobody is home when the appointment is kept. The record. What medium would hold it? Every physical record, stone, silicon, the arrangement of a galaxy, is itself part of the system, and the system's return is precisely the erasure of every arrangement it has passed through in between. Dyson, Kleban, and Susskind wrote this limit into their paper in a sentence of quiet finality. Discussing experiments that last longer than the recurrence time is meaningless, they observed, because the memory of the system has by then been erased. Sit with the shape of that. The recurrence is a return of everything, including every notebook, every instrument, every neuron that might have testified to the difference between the first performance and the second. A perfect return destroys, by definition, all evidence that it is a return. The event is real, on the sealed reading, and structurally private, without exception, without end. What does it mean that the most mathematically certain event in this entire story, guaranteed by theorem, priced by equation, is also the one event in physics that cannot, even in principle, leave a witness? This is the point where a working physicist reaches for an uncomfortable word: testability. Science's power has always come from a simple contract. Claims must face measurements that could, in principle, contradict them. Where does a guaranteed but unwitnessable return stand with respect to that contract? The field itself is divided, and honestly so. One camp holds that the recurrence theorem's cosmic application is physics in the fullest sense. It follows deductively from measured premises. If the premises pass their tests, the conclusion inherits their credentials, witnessed or not, exactly as we trust the interior of a black hole without visiting it. The other camp notes that a claim which no observation could ever check, whose confirming event erases all confirmation, sits closer to mathematics, or to metaphysics, than to laboratory science. True, perhaps, but true in a sense that has quietly left the contract behind. This channel will not pretend that dispute is settled. It is one of the open questions this topic leaves on the field's table, listed in the review literature, alongside the nature of dark energy itself. But now turn the picture 90 degrees, because there is one version of the return that does not have to wait for any tower of tens, and we already met it. Tegmark's counting did not schedule the repetition in time, it placed it in space, now. If space extends far enough beyond our horizon, and if matter out there is dealt from the same finite catalogue at the same odds, then the arrangement that is you, saying tonight's word, is not a future appointment, but a present fact, realized at this moment, around 10 to the 10 to the 29 meters away. And again beyond that, and again, without end. No waiting, no erasure paradox, because nothing needs to recur. The copies simply exist, simultaneously, each as real as this one. The recurrence theorem's strange promise rotated from when into where. And notice what this version trades away for its immediacy. Exactly the same thing the temporal version lost. Your double is real, on this counting, and sits past a horizon that light will never cross, in a region accelerating away faster than any signal can pursue. Two copies of one arrangement, each provably beyond the other's reach, without exception, for as long as physics runs. The universe, on either reading, appears to permit repetition, and to forbid, with equal rigor, the repetition's discovery. Reality and verifiability, pulled apart by the same expansion, in both directions at once. I return to this point often, and not because it is comfortable, because it is precise. We have spent the night among numbers that erase all human scale, towers of tens, digits numbering in trillions, distances that make the observable universe a dot. It would be easy to file the whole subject under the safely abstract. But the claims are not abstract. They are claims about the word you said 2 hours ago, the specific arrangement of air and neurons that made it. Physics of the first rank, published in the leading journals of the field, is genuinely divided over whether that arrangement is a one-time event, a scheduled rerun, or a pattern already playing elsewhere beyond all reach. That is not a small disagreement about far futures. It is a disagreement about what kind of thing a moment is. And one boundary must be drawn here with complete honesty, because the title of tonight's video walks up to it. Suppose the return happens, the full arrangement, your atoms, your memories, your half-finished word, reassembled to within an epsilon no instrument could fault. Is that you? Notice first what physics actually delivers and where it stops. The theorems speak of arrangements. They certify that the configuration recurs, indistinguishable by any measurement from the one sitting in your chair right now. Same atoms, in the sense that atoms of a kind have no individual identity at all, a fact quantum mechanics enforces with a rigor we have covered on this channel before. What the theorems do not contain, anywhere, in any equation tonight, is a quantity that tracks whether an experience carries over, whether the repetition is a continuation or merely a twin. That question belongs to the philosophy of personal identity, where it has been argued for centuries without a measurement ever being wagered, and this channel will not smuggle an answer into your ear disguised as physics. What the science says is exactly this much. If the premises hold, an arrangement physically identical to you, mid-word, occurs again, and whether identity of arrangement amounts to identity of person is a question no experiment on tonight's table can touch. Both readings are consistent with every equation you have heard. Physics prices the reprinting. It is silent, completely, on who reads the copy. So before the closing weighs it all, take one breath with something ordinary. Whatever the verdict, here is what did not change tonight. The coffee cooled and will not reheat itself. The egg stays broken. Tomorrow arrives once, on schedule, and every practical clock in your life keeps its old contract. Boltzmann's truce holds to the last measurable digit.
The second law rules everything a human will ever touch. What tonight has moved is only and entirely the word never, the difference between a door that is locked and a door that is bricked over. Nothing in your life passes through either. But it matters, more than almost anything, which kind of door it is. Ask yourself before the final weighing, which universe would you rather inhabit? The one where this moment is written once, or the one where it cannot stop being written? Hold your answer. Then see how close the evidence comes to giving you the other one. Now the threads come home. At the start of tonight, I asked you to say a word, and I told you a theorem claims the moment of saying it must return. 2 hours later, you know exactly what stands behind that claim, and exactly what stands against it. So weigh it the way the evidence deserves. What is actually proved? This much, and it is permanent. In any sealed, finite system whose laws conserve the catalogue of possibilities, return is not likely but mandatory. Poincaré established it for classical mechanics in the corrected Memoir of 1890. Boltzmann and Liouville extended it, stricter and cleaner, to any quantum system with discrete states. Cats priced the weighting, and a beaded string on a desert computer caught the machinery running in real time. No one in the century and a third since has found a flaw, because there is none to find. That mathematics will outlive every objection and every one of us. If you remember one sentence from tonight, this one has earned the place. A finite state space only has so many places to go. What is actually in question? Whether the universe is such a system, and there the evidence speaks with a leaning, not a verdict. Line the 4 resolutions up one final time and watch what each requires. The literal return requires a cosmological constant exactly constant, a state space exactly finite, and a fluctuation picture exactly literal. 3 coin flips, all heads. Its own architect titled the result disturbing and called for the assumptions to be revised. And the Boltzmann-brains census stands as the smoke alarm no one has silenced. A sealed, rereading library predicts deluded witnesses outnumbering honest ones without limit, and a theory that impeaches its own observers has failed the only kind of test it can face. The open drain requires just one thing, that the acceleration measured since 1998 keeps its character, and everything else follows with bookkeeping. Horizons that carry the library away faster than it can be read. Redshifts climbing past 5,000, past 10 to the 53. An information budget that closes. And Tipler's theorem waiting at the bottom to certify that in an open, ever-expanding universe, no trajectory returns. The still vacuum, if its reading of quantum mechanics is right, cancels the drama at the root. Nothing fluctuates, nothing recurs, nothing happens at all in the far dark. Though the theorem's own modern custodian disputes the reading, and the dispute is live. And the broken measure reminds us that if inflation truly never everywhere ends, the arithmetic of how often has no defined answer to give. Notice the asymmetry that has been assembling all night. Every road to the return runs through every one of the contested gates at once. Every road away from it needs only one gate to swing. On the evidence as it stands, the measured acceleration, the unresolved paradoxes of the sealed picture, the failed census it drags behind it, the weight comes down, and this channel will say so plainly. The universe, as currently observed, leans open. The library leans unbounded. The moment you are living leans unrepeatable, not because the theorem bends, but because the sky appears unwilling to meet its premises. And yet the belief you walked in with, gone is gone, once means once, does not get to declare victory either, because the two hinges the question turns on are named, real, and undecided. The first is a number, W, the character of dark energy, where exactly -1 seals the library and any drift at all unseals it, and no measurement can ever certify exactly. The surveys can only tighten the interval around the answer, decade by decade. The second is a structure, whether the true quantum description of our cosmic patch runs on finitely many states or infinitely many. A question tangled with the deepest unsettled issue in quantum theory, what the wave function is. And unlike so many questions at this altitude, the first hinge is being worked on right now with hardware. The same kind of surveys that discovered the acceleration in 1998 have successors in operation and under construction. Instruments mapping millions of galaxies and thousands of supernovae precisely to track whether the dark energy's character has drifted across cosmic history. Every data release tightens the interval around -1, and a confirmed drift in either direction would settle tonight's question overnight. A dark energy that changes is a wall that moves, and a wall that moves is no wall in Poincaré's sense at all. The second hinge waits on theory, on what quantum gravity finally says a horizon-bounded patch of universe is, a question the holographic ideas of Maldaceno's generation were built to answer and have not yet closed. Until those two are resolved, the honest status of cosmic recurrence is the one the review literature gives it, a rigorous theorem of contested applicability, proved as mathematics, unproved and currently disfavored as a description of the sky. Remember the beaded string one last time though, before treating the lean as a law. The first frames of that experiment also showed a clean verdict, and the longer film reversed it. Physics has been humbled before by exactly this kind of extrapolation. The lean is real. The lean is not a proof. There is one more edge past all of it, and honesty requires naming it before the end. Every argument tonight, every theorem, every census, every tower, begins with something already in place. A catalogue of states, laws that turn its pages, a universe for the counting to be about. Why there is a catalogue at all, why the pages turn, why anything sits still long enough to recur or to vanish, that question stands entirely outside every equation you heard tonight. The physics can trace the moment's trajectory forward through towers of tens. It cannot say why there was a moment to trace. That edge is beyond what the measurements reach in either direction, and the only honest move, the one this channel exists to model, is to say so and leave it standing open. If you found value in this exploration, consider subscribing. It helps these deep dives reach more curious minds, and the questions ahead, and there are more of them than there are answers, deserve minds that want the argument whole. So, the word. The one you said 2 hours ago, before the theorem, before the towers, before the sky weighed in. Here is where the evidence leaves it. If the constant drifts, if the library grows, then that word was a first and only printing. An arrangement the universe assembled exactly once in all the time there is, and will now spend the rest of time carrying away. Which makes the ordinary sentence you spoke rarer than any number this night could write. And if the constant holds, if the walls are real and the catalogue closes, then the word is not gone at all. It is shelved, scheduled, waiting out a number with 4 stories of tens, to be spoken again by a you who cannot know it is an echo. Boltzmann, who priced the waiting first, chose his word for that schedule with a physicist's whole heart, comfortingly large. Take the comfort either way. A universe that cannot repeat you has made you singular. A universe that must repeat you has made you permanent. Say the word once more, and notice what it has become. The shortest experiment ever run on the question of whether anything can happen twice, still running with the dice, tonight, in the air.